Alright, here are the problems on work, power, and energy, and I had to record it today. First question talks about a 55 kilogram hiker starts at an elevation of 1600 meter, climbs to the top of a 3300 meter peak. What is the hiker's change in potential energy? And what is the minimum work required? Can the actual work be more than this? Straightforward question, because you know that potential energy is mgh. So the change in potential energy is just mass multiplied by the acceleration due to gravity multiplied by the change in height. Okay, so that's a 55 times 9.8 times the change in height. And that gives 9.163 times 10 to the 5 joules. Now the B part, what's the minimum work required? Well, the minimum work required is equal to the change in potential energy. So it's the same answer. Can the actual work done be more than this? Yes. Why so? Because there could be friction and there could be other opposing forces that we have not considered. So this is the minimum work required, and in reality you would need to do a little bit more than this. The second question, a spring with the spring constant 53 Newton per meter hangs vertically next to a ruler. The end of the spring is next to the 15 centimeter mark on the ruler. If a 2.5 kilogram mass is now attached to the end of the spring, where will the end of the spring line up? Okay, when you apply force to a spring, it's going to get stretched, and in this problem what we got to find is how much it stretches and then add that extension to 15. That's all. Now F is equal to Kx, or K delta X. K is the spring constant. Now remember that 2.5 kilograms creates a force of 2.5 times 9.8. And if you divide that by K, you will get the extension. So well, that's how you get it. And delta X is, alright, K is 53. So delta X is 0.4623 meter, which is 46.23 centimeter. Therefore, the spring will line up 46.23 plus 15, because it was already at 15. That's 61.23 centimeter. In the third question, a 65 kilogram trampoline artist jumps vertically upward from the top of a platform with a speed of 5 meters per second. How fast is he going as he lands on the trampoline 3 meters below? Well, the figure is not given, but it's understandable that the platform is above the trampoline. So when the person jumps off the top of the platform, he has a speed of 5 meters per second, which means the person has kinetic energy. And because he is at a height of 3 meters above the trampoline, he also has potential energy. So on the platform, when he just takes off, he has both potential energy and kinetic energy. But when he lands on the trampoline, he only has kinetic energy, because we are measuring the height from the trampoline. That must be clear. So that's the first part. Okay. you have the platform here, the person there, and that's the trampoline. So at this point you have both kinetic energy and potential energy. At the top, that is 1/2 times mass times velocity squared. Okay, let me write that formula down. Plus mgh. When you do that, you get 812.5 plus 1911, that's 2724 joules. Now when he lands on the trampoline, he only has kinetic energy. So that's 1/2 times mass times velocity squared. Okay, and potential energy is 0 because the height is 0. Now the total energy has to be conserved, so both of these have to be equal to each other. So set them equal to each other and calculate the velocity. And it's 9.15 meter per second. In the second part of the question, the trampoline behaves like a spring, and the spring stiffness constant is 6.2 times 10 to the 4 Newton per meter. How far does he depress it? Now what's going to happen is when he lands on the trampoline, he has kinetic energy, and all that kinetic energy is going to be converted into elastic potential energy. So all of the kinetic energy is equal to the elastic potential energy, which is 1/2 k delta x squared. Okay. So therefore, you can calculate delta x simply by rearranging it. You get as 0.087. That's going to yeah, when you take the square root, it's 0.296 meters. Okay. Number 4, a projectile is fired at an upward angle of 45 degrees from the top of a 265 meter cliff with a speed of 185 meter per second. What will be its speed when it strikes the ground below? When the projectile is fired from the top of the cliff, it has both potential energy and kinetic energy. But just before it strikes the ground, it only has kinetic energy. So we're going to say the total, okay, that's a cliff, and let's say that you project it from there. And now I'm finding kinetic energy at the top is 1/2 times mass times velocity squared. Mass not given. It's going to get cancelled at the end. Potential energy is mgh. And the height is 265. So the total of the two is, you just got to add the 2. Mass is taken out as a common factor. And then you have 185 squared by 2 here, plus 265 times 9.8. And total energy at the bottom, it only has kinetic energy, so that is equal to 1/2 times mass times velocity squared. Now set them equal to each other. The masses get cancelled. And when you find the velocity, you get 140.4 meter per second. Oh, was that a wrong number? Okay, I need to correct that. It's 198 meter per second. 198 meter per second is the answer. Number 5. A vertical spring K is attached to a table and is compressed down. What upward speed can it give to a 0.30 kilogram ball when released? and how high above its original position will the ball fly. You're compressing a spring so it has elastic potential energy, and when it's released, all of that is going to change into kinetic energy. So that's the first part. The potential energy of the spring, 1/2 kx squared, is equal to 1/2 mv squared. Okay, the halves gets cancelled, then rearrange and find the velocity. Gives you 71 point, no, you have to take the square root of that, 8.44 meter per second. In the second part, as the ball flies up, all of its kinetic energy is going to change into potential energy. So now you're going to say its kinetic energy, which is this, is equal to its potential. And find the height. .634 meter, and that is easily understood. Number 6. A cyclist intends to cycle up a 7.8 degree hill whose vertical height is 150 meter. Assuming the mass of the bicycle plus cyclist is 75 kilograms, calculate how much work must be done against gravity. Now, how much work must be done against gravity? That's mgh. So let's do that part first. 7.8 degrees. And when you take sine 7.8, it's going to be x by 5.1, but that's x. And so that gives you the value of x, which is the height, because work done is equal to mgx in this case, because height is represented as x in this case. Okay, so 75 times 9.8 times 0.69, and that gives you the answer to the first part. Okay, I just changed it to h so there's no confusion. Now in the second part, we need to understand that the circumference of a circle is 2 pi times the radius. The second part, it's talking about each complete revolution of the pedals moves the bike 5.1 meter along its path. Okay, and the pedals turn in a circle of diameter 36 centimeters. So I'm trying to find out the circumference of the circle made by the pedals. Radius is 18 centimeter, which is 0.18 meters. So that's 1.13 meter. Work done is force times displacement, and therefore the force is work divided by displacement, and we know that the work is 507 joules. Now the displacement is 1.13, therefore it's 449 newtons that must be applied. 449 newtons that must be applied. Okay. This is a really easy one. A 145-gram baseball dropped from a tree 13 meters above the ground. What speed would it hit the ground if air resistance is ignored? If it actually hits the ground with a speed of 8, what's the average force of air resistance? Okay. Up there in the tree, it has potential energy, which becomes kinetic. So you don't need the mass of the ball right now, and you can find the velocity. Two times 9.8 times 13, and you get it as 15.96 meter per second. In the B part, it's actually hitting the ground only at 8 meters per second. So now we can find the kinetic energy at the bottom. And the idea is to find the loss of energy, okay? So let's find the kinetic energy at the bottom now. You get it as 4.64 joules, and potential energy at the top is mgh, and that'll give us the energy that it had initially. Which is 18.47. So now find the difference. When you find the difference, that is going to give you the energy lost. And energy lost is the work done by air resistance. So once we get that, we're going to say that's the work done by, little tiny mistakes there, I've corrected it now. Work done is force times distance. I'll have to change that. And so force is work by displacement, right? Okay, let me change that to 13.83 by 13. That gives 1. Yeah, it's almost 1 Newton. That's the force exerted by air. Okay. Alright, number 8 is a good question. A skier traveling 12 meters per second reaches the foot of a steady upward 18-degree incline and glides 12.2 meters up along the slope before coming to rest. What is the average coefficient of friction? Again, you find the change in energy, the loss in energy, okay? So that's 18 degrees, that's 12.2 meters, and the skier is going up at 12 meters per second. The kinetic energy at the bottom is given by this formula. Mass is not given. It doesn't matter. It's going to cancel out. Velocity is 12. So you get 72 m. Remember, this is not 72 meters. It's 72 times the mass. And potential energy at the top is mgh. H is 12.2 sine 18. Yeah, because it's opposite side by hypotenuse is sine 18. So that comes out to be 3.77. Therefore, mgh is 36.95. Therefore, the loss is 72 minus 36.95. And that must be the work done by friction. Therefore, work is force of friction, which we're trying to find, times the work, the distance, which was 12.2, wasn't it? So when you rearrange, you get that as force of friction as 2.87. But now remember that if we make the diagram, if we complete the diagram, the normal force here would be mg cos theta, because mg would be acting straight down, and when you resolve it, you would get this as this component here is mg cos theta. I'm not writing it there, but it's understandable. So that gives us Fn, and that's 9.32 m, and coefficient of friction is frictional force divided by Fn, the normal force. Okay, so divide that, the masses get cancelled, and we get 0.31. That is the coefficient of friction. Ninth one, during a workout, the football players at State University ran up the stadium stairs in 66 seconds. The stairs are 140 meters long and inclined at an angle of 32 degrees. The mass of a player is given. Find the average power. First, we got to find the work. Okay. And in fact, first, let's find the height, because that's 140. H is 140 sine 32. That gives the height as 74.2 meters. Power is work over time, and in this case, because they're lifting themselves up, work is nothing but increase in potential energy, which is mgh. So mgh by time. 95 is the mass. H is 74.2 divided by the time, 66 seconds, and you get the power. 1047 watts is the power. Brings us to the last question. Which is the best one? A bicyclist coasts down a 7-degree hill at a steady speed of 5 meters per second. So he's going down. What's interesting is that the speed is steady there. Okay, let me not use that. All right. The speed is constant. Why is the speed constant? It's because the net force is 0. Because that means there is no acceleration. Which would mean that the force of friction is exactly balancing mg sine theta. Because we know that when an object moves along an inclined plane, there is mg sine theta acting down. Okay, let me get this now. Mg, this is mg sine theta. Stop. Let me just write this as mg. Alright. So mg sine theta is acting down. Friction is acting up when it's coasting down. Alright. Power is work over time, but work can be written as F times delta x. So now you get a new formula. Power is force times velocity. Force is mg sine theta. Mg sine theta times 5 gives 448 watts. Now if it's going up, he has got to fight both mg sine theta as well as friction. And therefore his actual power is going to be twice this. It will be 2 times 448, which is 896 watts. Now this problem takes a little bit of thought, and I hope you understood. Now let me repeat and say that when it's coming down, friction is up, but mg sine theta is down. Okay? When it is going up, both mg sine theta and friction are down. So this guy has to do double the work. Therefore, he has to have double the power. I hope that makes sense. These are 10 good questions, and we'll let you prepare for this exam. Thank you.